So let's say we had this triangle, and let's just say it's right here, right? We have a right triangle, okay? A right triangle. And yes, it's a right triangle, so I'm going to have that. And let's say I make a couple more right triangles out of this right triangle. And the way I do that is by drawing an altitude of the triangle, or draw a height of, and I'm going to call this triangle A, A, B, no, I'm not going to do that, actually, an idea. Triangle ABC. So this is right triangle ABC. And I'm drawing a couple more right triangles out of this right triangle. And I am going to call these triangles, I'm going to call this point D. So, another thing, I'm going to say that this right here is side length A. And I'm going to call this side length B. And I'm going to call this entire thing right here side length C. What is the relationship between side A, B, and C of a right triangle? How can I find that thing? Now, the first thing to keep in mind when trying to find the Pythagorean theorem is you don't want to focus on this length right here. And there are multiple ways to prove the Pythagorean theorem. I don't really know them. I'm just going to show you one way that I don't know, just one way to do it. And it's using similar triangles, similar right triangles. Now, which triangles do you see that are similar here? Which ones of these right triangles are similar to each other? Now, if you look closely, you're going to notice that every single one of these triangles are similar to each other. So every single one that's here. So that means I'm talking about triangle ABC, which I'm going to say, triangle ABC, triangle ACD, and triangle CBD. All of them are similar. So let me just say that, right? I'm going to write it down so I can use it, or I can know what I need to care about. So triangle ABC, triangle CBD, right? So triangle is similar to triangle CBD, right? So triangle ABC, CBD. Another thing, I'm really gonna care about this main triangle. I don't care about triangle. I don't care about this small triangle being similar to this small triangle. I care about the whole triangle that's around here because that's the sides I'm drawing a relationship with. So triangle ABC is similar to triangle, CBD, but also, which way does it go? CAD or ACD? I'm pretty sure it goes ACD. Triangle ACD. Yes, it does go that way. Now here's the thing. How do we know that they're similar? Well, we can use angle similarity, or just angle to show that these triangles are similar. I'm not going to go do a full-on proof. I don't care about that. They each have a right triangle. They each have a right angle. Each of these triangles have right angles in them. So a right angle here, right angle here, right angle here. That's one of them. Now in triangle ABC, they both share angle B. They both share that angle. And so that means that they pretty much, you could say that's the reflexive property right there. So I could do that, but I'm not going to do that, right? Reflexive property at angle B. And so that's angle, because two of the angles are congruent. Now here, ABC and ACD, they both have angle A, which are congruent to each other. Okay? Now you could be more accurate and really see that if you're doing a triangle that looks like this, because then you're really going to see that more easily than if you had something that looks like this, right? It's more easy to see how it's ACD and not CAD, right? I can say ACD, or is it CAD? It's more easier to see if you draw a steeper right triangle. So if that's not clear, that's my fault. But we have this, and we know that each of these triangles are similar to each other. And we care mainly about triangle ABC. Now, what do we do next? Now that we know that these are similar to each other, we are going to use side lengths to pretty much draw a relationship between A, B, and C. And remember, we're going to ignore CD when drawing these relationships. Now let's focus on the sides of triangle ABC and triangle CBD. So let's focus on these two triangles first. So we could say, looking at this triangle, triangle CBD, we could say that BC is to BD, so I'm going to write that down, BC is to BD as, so BC is to BD as BA is to BC, right? As BA is to BC. And if you're confused about how that works in the image, it's perfectly fine to just look here. BC is to BD as BA is to BC, right? It's just making sure that they're pretty much following the correct order. So looking at these two triangles, you could say, oh, well, AD is to AC as AC is to AB, right? So AD is to AC, so AD is to AC as AC is to AB, right? Right? So we're pretty much drawing proportions of the sides. So proportion of the side lengths between each of these similar triangles. That's what we're trying to do. Now, why is this useful for A, B, and C? Now remember, A is just BC, so BC is A. So if we solve for BC, I could say, well, if I were to cross multiply, I get BC squared equals BA times BD. If I were to cross multiply here, I get AC squared is equal to AB times AD, right? Now there's the thing, AB and BA are of course the same thing, so don't treat those things as separate. So I'm just going to do that. AB, AB, and that's basically it. Here's another thing. BC, I'm going to pretty much add BC squared plus AC squared. Why am I doing this? Because you're going to see what happens when I do that, right? That's basically the way I like to show what's going on. So BC squared equals AB times BD, right? I can add AC squared to both sides, right? We can do this. This is fine. This is the addition property of equality. But if we're adding AC squared to both sides, couldn't we add AC squared to one side and add AB times AD to the other side? We can do that. It's still the addition property of equality because those things are equal to each other. So I'm going to add AC squared to one side and AB times AD to the other side. Now here's the thing. AC squared plus BC squared, or BC squared plus AC squared, is just A squared plus B squared. So I'm going to write that as A squared plus B squared. Notice how right here I have AB, I could factor out AB, and I'm left with BD plus AD, right? Now AB is C, right? This is C. But isn't BD plus AD also C? So this is just C times C, or C squared. So A squared plus B squared equals C squared. And so you can derive the Pythagorean theorem using these similar right triangles and the proportion, or how the side lengths are proportional to each other for each of those similar triangles that we made here. That is how we derive the Pythagorean theorem, one way anyway, to do that part of it. Yeah, that was good. Yes.